Hello, this is Dr. Viv. In this video, I'd like to discuss uniform circular motion. I will talk a little bit more about motion that's not uniform and that's not exactly circular at some point, but right now, at least for the setup, I'm going to assume that there is a particle moving in a circle of radius r. I have purposely labeled these points A and B so that we can talk about them as 2 points where the distance between A and B comes close to 0. So what we can do is move this vector VB to where VA is. Vectors can always be moved parallel to each other. So I'm moving this vector parallel to itself where this vector VA is located. So I'll call this VB. Put arrows on all these vectors. Now what you'll notice is that the vector that joins VA and VB, which I will call delta V, is approximately pointing towards the center. It won't exactly be pointing towards the center, but because my diagram is lousy, it appears to point to the center even now. In reality, it will only point to the center in the limit that A and B come together. So let's write down the equation that describes this vector process. Now by vector addition, VA plus delta V must equal VB because the vector VB is got by joining the tail of VA to the head of delta V. So VA plus delta V must equal VB. Well, that immediately tells us that delta V is precisely the difference between VB and VA. So what I've done here is I've subtracted VA from both sides. Now you can think of this as the final and that as the initial. So the acceleration is defined as a limit as delta t goes to 0 of delta V by delta t. In that limit, it becomes dV by dt. So this is the well-known definition of acceleration. Now, because I've considered the motion to be uniform, I'm going to take the magnitude of VA and the magnitude of VB to be equal. Let me call that simply V. And also, since I'm considering the motion to be in a circle, RA is equal in RB to magnitude. I put double for magnitude sometimes instead of the single bar. So that's going to be called the radius of the circle R. With all that in mind, let's now take a look at this picture again, more careful look. This angle theta actually makes an appearance here as well. And the reason for that is that if the angle between the two radius vectors is theta, then because the velocity vectors are perpendicular to the radius vectors, the angle between the two velocity vectors must also be theta. So you can see this is 90 degrees, and that's 90 degrees. So all I'm doing is shifting something that has a fixed relationship to the radius over to that side, so that angle subtended between the two radii must be the same as the angle subtended between the two velocities. Now what we're going to do is compare this almost triangle. It's actually the sector of a arc, sector of a disk. We're going to compare that with this triangle. Now in the limit that A comes very close to B, this actually becomes a legitimate triangle. Now to help us in this, we're going to invoke some results from what I call arc geometry. Okay, there's a fundamental result in arc geometry that the length of the arc, which I'm going to call delta S, remember I'm calling it delta S because it's the length between A and B, let the radius of that circle be r. So you should think of this as some pizza slice. Then we have by the arc geometry, theta equals delta s divided by r. Now also you can think of this as an arc. Even though it's a triangle, you can think of this as a little arc. So I'm going to write that is also equal to the magnitude of delta v, which is the length of this vector, divided by the length of this. And that's just going to be v, okay, because the length of one of those vectors is v. So I have this interesting looking object. Now what I'll do is divide both sides by delta t. Actually, at this point I don't care about theta. This just helps us establish the proportional relationship. Theta is equal to delta s over r by looking at this sector, and theta is equal to delta v over v by looking at this triangle as another sector. So once that's finished, theta's job in life is complete, so we'll ignore it. What I'm going to do now is divide both sides by delta t. Delta t is the time taken to go from A to B. So if I do that, I get delta s over delta t times 1 over r is equal to delta v upon delta t times 1 over v. All right. Now I'm going to take the limit as delta t goes to 0 on both sides. Delta s over delta t is just the speed, v. So on the left hand side, I'm just going to get v over r. On the right hand side, delta v over delta t is the magnitude of the acceleration. So I'll call this a. So if you have a beautiful equation here for the acceleration, this gives me acceleration equals v squared over r. This acceleration is sometimes called the centripetal acceleration, so I'll subscript it with a sub c. The idea behind centripetal acceleration is that it's always pointing towards the center of the circle. So if you have a circular motion, or now I'll be more general, any motion, but let's suppose you have any motion, but you can fit circles of radius r over portions of that curve. Then you can make the statement that as long as the velocity as it's going on that curve is v, at any instant, the acceleration is going to be towards the center, and it's called a sub c with that magnitude. Now, as this particle goes on other portions of the curve, it's going to have different radii of curvature and different speeds, perhaps, but you can use this formula locally at every point. So that's the generalization I spoke of to things that are not circular. All right, let's use the formula for centripetal acceleration to solve a elementary problem. Later on, we'll combine this with Newton's second law and solve more substantial problems. But at this stage, I just want to solve a simple problem. So here's an example. I have something, a toy car, for example, moving in a circle. So this car, which I'll call C, starts from rest, and it moves with an acceleration along the track. It's forced to move in this track, so you can imagine a little motor toy, and let's call that acceleration along the track a naught. All right. Now after a time t, the car is located here at a different point. Let's call that point P. I want to find the net acceleration at point P. Later on, we'll see how this is related to the force needed to keep the car in the track. But right now our aim is very, very simple. Find the net acceleration at time t. The net acceleration is comprised of two separate accelerations. One is going to be the acceleration which the car has got, a naught, from simply having a motor with that acceleration. Then at this point, it's going to acquire some speed by the time it comes from C to P, so it's also going to have the centripetal acceleration, which I'll call a sub c. The way I've drawn it, a sub c and a naught are equal in magnitude, but in general it doesn't have to be. That's just my drawing. And the net acceleration is simply going to be the resultant of these two accelerations. It's going to point in some strange direction. Let's call this angle alpha. All right. So in a circular motion, there are two coordinates that are pretty important to talk about. One is a theta coordinate that tracks the tangential direction, and the other is the radially outward coordinate r hat, and its close cousin, the radially inward coordinate negative r hat. You can observe that the centripetal acceleration is always pointing in the negative r hat direction. This negative r hat simply means that if you go from place to place, whatever vector points towards the center of the circle is always in the negative r hat direction, and whatever vector points in the tangential direction is always in the positive theta hat direction. If it's going, actually this is negative theta hat, positive theta hat if it's going counterclockwise. So this is positive theta hat. So that's the general state of affairs for circular motion. Anyway, that's so much for the direction conventions. Let's focus on solving this problem. The tangential velocity from the first kinematical equation is the velocity at time 0, the tangential velocity at time 0 plus a naught, which is the acceleration of the car, times t. I said the car starts from rest at point C, so that's 0. This tells me the speed at point P is actually a naught times t. The centripetal acceleration, therefore, is that speed at point P divided by the radius, squared divided by the radius, using that formula. So I'm going to get a naught squared t squared divided by r. Now, the total acceleration, a, and now let's try to be vector savvy, is going to be a naught in the well, the car goes like this, so it's going to be a naught in the negative theta hat direction, and then it's also going to be plus, it's going to be a sub c in the negative r hat direction. Okay, so let's put the values here. That's going to be negative a naught theta hat, negative a naught squared t squared over r hat. So that's the acceleration written as a vector. If you want to find the magnitude of the acceleration, all you have to do is use the Pythagorean theorem, and that magnitude is just going to be the sum of the squares of the components. So I'm going to get a naught squared plus a naught to the power 4 t to the power 4 over r squared. As expected, the magnitude of the acceleration increases due to this tangential factor increasing with time. You can also go ahead and find alpha if you want, using tan alpha. So tan alpha is going to be the opposite side, which is a naught, over the adjacent side, which is a sub c. And the magnitudes of a naught and a sub c are known to us. It's over there. So I'll write it as a naught over a naught squared t squared over r. So we can write tan alpha as r over a naught t squared. So that completes the description of the problem, where alpha is the angle between the acceleration and the inward normal. Observe that the units work out here, because the units of, so let's just pay attention to some units here. The units of tan alpha should have no units because it's just a number. It's going to be meters over a is meters per second squared, and t squared is second squared. So sure enough, it has no units.